Hello and welcome back to CCCS214 Object-Oriented Programming 2, and we are continuing our study of multithreading in Java. So last time we looked at the use of raw threads and the use of thread pools using the executor service in Java to write multi-threaded programs. Now, one thing that we didn't talk about and that we'll cover today is thread synchronization. What happens if you have a situation in your code where having two threads operate on the same variables on the same data can cause problems. Now, we haven't seen such a situation yet, so let me show you an example. So let's say we have a program in which we maintain a variable called balance, like the balance of a bank account. And we can have multiple threads. We are allowing multiple threads to change that bank balance. And let's also say that to change the bank balance of the account, two things happen. First of all, we read the current balance, make some change to it. In this example, we're only going to increase the bank balance by 1, and we get a new total. Let's call it new balance, and this is the first step. And then we want to write that new balance. We want to save that back into the account. And let's say for that, in the second step, we call a method called setBalance, which sets the balance of the account to this new value that is 1 larger than what it was before. Now, if we allow this to, if we're doing this in a single-threaded program, there's obviously no problem, nothing to it. But let's say we can have multiple threads of this method, that updates the balance of the account. And we could end up in a situation like the one that you see on this slide. We have one thread over here, let's call it thread I, and we have a second thread over here, let's call it thread J. And let's say the first thread, thread I over here, reads the current balance in the account, adds 1 to that number, and stores what is going to be the new total in new balance, a local variable of that method that is doing this update. And after that, control passes to the second thread, thread J, which does the same thing. Now, new balance is a different variable for the second thread. It's a local variable. Now, it too gets the balance, which is still the same that the first thread saw, adds 1 to it as well, and stores the value in its own local variable, new balance. So remember, this new balance variable is distinct, is separate, is different from this new balance variable over here. And then control of the thread passes back, control of the CPU passes back to the first thread, which then calls the setBalance method on the account and writes this new balance value into the account. So what ends up happening at this step 3 over here, the actual account balance has gone up by 1. And then finally, in the fourth step, control of the CPU goes back to the second thread, and it does the same. Now, the problem is that although we did 1 increment over here in this thread and 1 over here, both threads updated the same, or incremented, added 1 to the same value of the bank account, of the balance. And what ends up happening here is that instead of seeing, as we would expect, an increase of 2 in the account balance, we will see an increase of only 1. Now, to show you this, let me show you the whole example now, the code for this whole example. So this example is called account without sync. Let me explain the structure of this. So we have uh, a method. We have a task, actually in the form of a class called add a penny task, which has a run method, which is basically this thread that we just saw in this example, which is going to increment the bank balance by 1 every time it runs. And we're going to call this run method 100 times. So we start off with a balance of 0, and by the time our code finishes executing, we expect the bank balance to be 100. The balance is kept inside of a second class called account, which has a get balance method, which we just saw, and a deposit method, which is basically where the change to the bank balance occurs. And all of this is happening inside of a test program with a main method called account without sync. So this example is going to show you the problem of what happens if you have a program such as this one, where two threads updating the same variable might cause problems. So this example is going to illustrate that problem. So let me walk you through the code. So we have over here account without sync. Let's start with the main method. In the main method, in the class account without sync, I have one member variable. I have one object of the class account. Okay, and so this is kind of like a global variable. You can access this and any object inside anywhere in the main method. I can access this account object. And so we enter the main method, and I have this executor service over here, which is the best thing that we know up to this point. And I'm using the new cached thread pool method. I'm not specifying how many threads are going to be in this pool over here. And this is actually the heart of it. We have a loop that goes from 0 to 99, so it goes 100 iterations of this loop, and in each iteration we call the execute method of the executor service object executor. So this is the same thing we did in the last example, in the last lecture, and we create an add a penny task object. Now remember, this is the one that actually does the updating of the account balance. Okay, we'll come to that. And so after starting these 100 threads, we're going to shut down this executor service after all 100 threads finish executing, and you can make sure of that by calling the is terminated method on the executor object. And when we're done, we call the get balance method on the account object to see what, after all 100 threads have finished executing, what the total balance in the account is. Ideally, that should be 100, but we'll see what it is. It's not going to be 100 because of how how the deposit method has been implemented. So the add a penny task is the one with the run method. So we're basically creating 100 threads of this run method, and inside of it we're calling the deposit method of the account object, and we're making a deposit of 1 every time. Here is the account class. Has only one member variable called balance, which starts at 0. The get balance method is simply used to read the value of the balance variable, member variable, and this is the deposit method that is being called from inside of the run method that's basically called by each of the 100 threads that we'll create. And what's happening is this, we simply add whatever amount is passed in the argument, in our case 1. We add 1 to balance and we come up with a new value called new balance. And just to show how bad the problem is, we're going to take some time. We add a delay in here just to make sure that this otherwise very short method takes a little time to, so there's so there's a delay between us reading the value of balance and computing the new balance and actually assigning the new value to the balance member variable. So we added a 5 millisecond delay in here using threads sleep method, which we again used in the last lecture. Okay, that's it. That's all. So let me run this example. And there you go. What is the balance? 3, not 100. 3. So apparently only 3 threads were able to run sequentially, one after the other. If I run it again, 3. Let me run it again. Still 3. 5. So you can see 7. So it's kind of random because we have no control. We impose no conditions on when one thread, when each thread is allowed to start execution. 4, 3, 5, 3. So you can see 6. We definitely never get to 100. 12. That's the best that has happened so far. Closest to 100 that we got was 12 with this. All right. So this situation that we have over here, where 2 threads are accessing this, or updating, reading and then updating the same variable at the same time, causing these problems. This situation is called a race condition. We have no control over when one thread is going to be executing and interrupting the other one, and this way the outcome can become or becomes unpredictable. Now, there are multiple ways of fixing this problem, and I'm going to show you first off a very simple method. It uses a keyword called synchronized. The synchronized keyword is actually, it's kind of the simplest solution in the sense, in terms of how much we have to modify our code. Basically, you can declare any region of the code that should only be run by one thread at a time, not multiple threads, but only be entered by one thread at a time. That region of a code is called the critical region. In our case, that is all of the deposit method. So this method, basically everything that's happening in here, from the first line to the last, this is our critical region. Only one thread should be running this code at one time, not 2 at a time, 1 at a time. If one thread starts executing this portion of the code from here, it must be allowed to finish before another thread is allowed to enter into this region. And one way to do that is by using this new keyword called synchronized. Now you can declare an entire method, critical region, by adding the synchronized keyword where you're defining the method. And that is really the simplest way of fixing this problem. If the method happens to be a static method and you declare that static method synchronized, not only will you be locking access to that method for all other threads, you'll be locking access to that method for all objects of that same class. Because remember, when you have a static method, or static variables in fact, those are shared across all or by all objects of that class. So in effect, what's happening is this. Once you declare a method synchronized, if you have one thread, one task that is running, it will basically be, it's kind of like acquiring a token, or we say in programming terminology, a lock on an object, on a method of an object, and only the thread, the task in this case, that has that lock is allowed to to execute that part of the code, and it is allowed to and until it finally finishes and releases that lock, or you can also think of that lock as a token. And then another thread, of this task 2 over here, may acquire that lock um, and execute the critical region of that code. So let's go back to the example that we had, and let me show you the simplest method of making sure this problem that we're seeing does not occur. We can simply declare the entire deposit method a critical region by adding this synchronized keyword right after public, in this case, public, private, whatever the case may be. So let me just rerun the same example again. I've changed nothing else. And there you go. What is the balance? 100. And let me run this a couple of times just to show you this was not a coincidence, or freak coincidence. You can see I can run it anytime, any number of times I want. The answer is always going to be 100. Now, instead of applying the synchronized keyword to an entire method, you can also apply it to segments of code inside of methods, to acquire a lock on an object. What you can do is you can use this syntax. Synchronize, so this can be anywhere inside your method. Synchronized, and as argument it'll take a reference to an object, and then you have a couple of statements, and you close the parentheses again, and anything inside these parentheses, all of these statements, however many they may be, these will be treated as a critical region of code. So if you want to go do it this way, so what we just did was we added the synchronized keyword right after public for the deposit method. So we basically did this first example, this first method over here. You could also do this. You could leave all of the code inside the deposit method over here, and you could use the synchronized. You could use synchronized with an object reference, like we just saw on the previous slide. These two methods are equivalent. They will do the exact same thing. So let me quickly demonstrate that as well. So we're back to our old deposit method without the synchronized keyword, and instead what I'm going to do is I'm going to select all of this code inside of the deposit method. I'm going to indent it, come back up here. Synchronized, and I'm going to acquire a lock on the object to which this deposit method belongs, and I'm going to close this right here. So just put all of this code inside this synchronized block. Let me run this again. 100, no problems. Let's do it a couple of times. And there you go. So these two are equivalent. Now, I already used the word lock. Another way of doing things is that gives you a greater level of control is by using the lock class, the lock interface yourself. I'm sorry, the lock class which implements the lock interface. So let me show you one more way. Now, you may wonder, it's so easy to use the synchronized keyword and use a synchronized block of code. Why do things, why get into the nitty-gritties, details of locks? One reason you might want to consider it is gives you greater, you can have greater control over specific over how fairly different threads get access to the critical region. So let me show you another example that uses this lock class implementing the lock interface. This one's called account with sync using lock. And so this one uses locks, of course. And as you can see, so the name of the class is different, but we still have an account object as a member variable. We have a main method which has a loop, for loop for 100 iterations, inside of which we create one thread each of the add a penny task, and after that we shut down the executor object and we make sure everything's all the threads have terminated before we call the get balance method on the account object and print out the balance of the account. The add a penny task class with the run method is still exactly the same, just calls accounts deposit method and adds 1. And what's really different is the account class. So the account class over here has, in addition to the balance member variable, it has an instance of the lock class that we call lock with a small l over here, and we're going to use a subclass of that called a reentrant lock, and the constructor to that does not require an argument over here. The get balance method is still exactly the same, just returns the value of the balance member variable, and we use this lock that we added as a member variable to this account class, we use it inside the deposit method. And the change is small, but again in two places. At the start of the critical region of the code, we call the lock method of the lock. So this is like us, this is like thread obtaining a token, a key, a permission to enter the critical region. And after that, have the same code, just moved the update of new balance. We moved that into the try block that earlier contained only the sleep method of the thread class. Doesn't make much of a difference. And here in the finally block, even if anything, and why do we keep this in the finally block? Even if we get an exception for calling the sleep method in here, the finally block, remember, will always be executed. So this makes sure that even if anything goes wrong inside the try block over here, the lock is released in the end, so other threads may try to execute this part of the code. So let me run this and see what we get. Balance 100. So this works. One more time. No problems, as you can see.